Everyone. First of all, let's look into the questions which are given on assignment number 6. So, as you can see, there are some multiple choice, and most of them are like numerical based questions. And I will solve one of them. Not, I mean, not the same problem, but with the different data. How to solve this kind of this KPI low. I will solve one example problem so that it be easy for you to solve this kind of a question. So that in parallel universe following the regard. I have like I know how to solve this kind of a modeling problem. I mean, but they want just you to know the concept base. So I will solve related to one of the problem related to this only, or not, but no friction. Yeah, I think you will like it. So because most of these problem are related to TIVA microcontroller. So please, I would recommend you to go to this data sheets. Okay, so where are these data sheets are available? I will let you know. So there is this hands-on activity section, right? In that section, what you need to go, you need to go to that hands-on activity relevant material. You go to this section, there is this will open, and in this, you look into this Google Sheets are open. Okay? In this, there is this Siva microcontroller is given here. Here, all the data sheets are available here. Okay. So what you need to go is you need to go through this each of these data sheets. This is what the TIVA data sheet is. Okay, you need to download this data sheet. So I have already downloaded this data sheet, but I will just open that data sheet. I have just you need to open this data sheet that you can get a greater idea. So for QVI interface, you need to go to this chapter 21. Okay, and in this you will you will find this kind of other same picture which and there is I think there is one example problem is also been solved here. Something this problem you can play with. Okay, so they have solved this problem. Okay, so how to solve this? This will give you some idea how to solve this kind of a question. Okay, please, I mean, for QUI quadrature and quadrant interface, you need to go to chapter 21. Then there is, I think, there is a problem related to PWM also. Is the pulse width modulation. So you need to go to the chapter 20. Is the block diagram map. I think there is something for this. Yeah, so you will get this kind of a. There is one example problem is also given you. Okay, this all this thing will help you. Okay, just need to. I mean, you can't just spoon feed you everything. So you need to figure it out by yourself. Okay, so what I'm trying to do is please go through these data sheets. Okay, these data sheets I will again repeat it. What you need to you just need to go to this hands-on section. In that you will find this Google Drive. In that you need to find this data sheets. From these data sheets only you will get this diagrams, and there is one example problem is also solved for you, so it will be available. But I will also solve one problem so that you get an idea. So this was the yeah. So let's just start the today's session. Okay. If you have any problem, please do ask me. I think I have. Please write it on chat box, or you can unmute yourself and ask. So let's just start today's session, and at the end I can have any. Yep, so the first question is related to QEI. So I've already have this kind of a question. Just out the question. So it's a common data question. The TM4C123 data sheet. The data sheet which I referred you, you need to refer the page number of 1305 to 1309. Find this type of schematics. Okay, so let's just uh, read out what the question is. The microcontroller clock frequency is set to 40 megahertz. A quadrature encoder interface is a quadrature encoder is interfaced with QA module and having a resolution of 1024 pulses. Okay, so the encoder specification is given here. The encoder specification is given in PPR, which is pulse per revolution. So if you want to buy a encoder, right? When you just type in Amazon or any Robu, let's say, you can just type. So these are the main specification of a digital encoder. It's in PPR format. Okay, so what do you mean by PPR? It means that pulse per revolution. So after 1024 pulses, it will so after 1024 pulses it will measure one revolution. Okay, so suppose if you interface this encoder with a motor, and if you manually turn that motor one revolution, the quadrature encoder interface output will be 1024. Okay, 1024 pulses it will give. So let's just move on. 1024 pulses per revolution, and is used to measure the speed and position of a motor shaft. Okay, they want to measure a motor, and they are using this. If a velocity is to be obtained at an interval of 10 millisecond, okay, so what they are saying is like so the velocity they have to measure. Okay, and how to measure the velocity? So uh, what they want is like, so encoder is used to measure position, right? What they are trying to do is, suppose the S2 is the uh, initial position, is the present position, and S1 is the previous position. And when you divide it by delta t, you will get velocity, right? So this delta t is given to you, 10 millisecond, with the best accuracy possible. What is the value to be set in QEI load? Okay, so what is QEI? So this is what a QEI load looks like. Okay, so how this whole algorithm works for this whole microcontroller? You just need to go to that data sheet and read out 13005 to 309 pages, and you will get an idea. But let's just say you know what. So I will tell you what this Q is. So it's a register. Okay, so it's a register. Registers are basic. I've told you it's a 8-bit register. Then like this, right? These are register. So you need to put some value in it so that it can. So what is the value to be set in QI load register in binary? Assume that the application speed is sufficient high to get enough pulse of 10 millisecond. Okay. So whenever you see that there is a load register, you need to always write the answer in clock cycle. Okay, clock cycle. Okay, what is clock cycle? So if I tell you the clock cycle is, so in 1 second, so if a microcontroller is given, it's 1 second, it will run up to 40,000 uh, 40 megahertz clock cycle. So it's 40 into 10 to the power 6 clock cycle. Okay, so 1 second it can run 40 into 10 to the power 6 operations, basically just putting LED off and on and off. It can do that 40 into 10 to the power 6 times. That is what a clock cycle means. Okay, so whenever there is something you need to enter in register, it has to be always in terms of clock cycle. Okay, so how to convert that into a clock cycle? So from the question, it is in velocity timer. So this is what the peripheral of the module which we have in it to work. It's a velocity timer module, and in velocity timer module, it is given that it has to be activated at 10 millisecond. Okay. So what we need to do is we need to convert this 10 millisecond into a clock cycle. That is what we need to do. Okay, how to convert that into a clock cycle? Suppose in 1 second it is doing an operation of 40 into 10 to the power 6 clock cycle, right? So what it will do in 10 millisecond? Just to do 10 millisecond, 10 millisecond. So basically, how much clock cycle it will consume? That is what they wanted. Okay, so just multiply. So how much you will get? with 10 to the power, I think minus 2, and I think 14 power 6 is something like 40,000. So it will be around 40,000, I think. You always need to enter in clock cycle, okay? So that is what we have done. Just is just divided in terms of that to the power 6. So you will get around 40, not 40, it's 4 lakh clock cycle. So the QA load will be, the value will be 4 lakh clock cycle. But in the question it is written that it has to be written in binary, okay? So all binary operation we just need to minus 1, because in binary we also measure 0 as 1 cycle, right? Here the answer will be 4 lakh. If you have any question, please do ask me. You can unmute yourself, or you can, I think, write it in the chat box. So this is what the question is. You need to always enter in terms of clock cycle, okay? And let's just move on. So there is a follow-up question to the previous slide question. So with reference to the question number 1.1, both edges of phase A and phase B channel of encoder. So I think in week 2, Professor Gandhi has told you like the encoder has uh, kind of there are two phases, right? Phase A and there's phase B, and in that there is something called a phase lag is there. 90-degree phase lag is there. Okay, this is what we know, right? So with reference to the question 1.1, both edges of A and channel both phase A and channel B, channel phase B of the encoder are used for speed calculation, and edge count per second is given to you. So here edge count per second is given of what is the speed of the motor in RPM. Okay, so we need to first understand what is this edge count per second. So when you have this, so one clock cycle, I mean one time period is from here to here, right? And then the signal repeated. And what is edge count? Okay, you need to understand what is edge count. So what they are trying, so what is edge count? So I've told you that in quadrature encoder interface, they, in one clock cycle there have four pulses, right? Like one pulse is here. They will measure. So for one pulse, they have something called. If you have one pulse, the signal will be four. What they do is like they divided the whole pulse into four. So suppose if a motor, if a encoder run for a half cycle, suppose if a motor runs up to like 0.005 degree, okay, so it will run up to this. In that case, the value will be 2, because they are detecting two pulses, 1 2, like that. So here so the edge count per second is basically how many reading which are coming from encoder. Okay, here it is given, which is 4096. Okay, and you need to convert that into a speed. What is it? What is given? Quadrature edge count per second is 4096. It is given to us, and we need to calculate RPM. Okay, so how to calculate, how to proceed this kind of a question? Can anybody, I mean, say some? Uh, have an objective type question exam? No, actually, you don't have an objective type exam. There will be a numerically based exam also. So just like it is given in this assignment, you can see that this type of question, the numerical ability question, AT, numerical ability type question. This type of question can also be asked in exam. That's why Yeah, I'm sure. So yeah, so where was I? So yeah, so you have this. This is given to you. This is what your encoder is giving to your micro. So and so I mean, how it is given. I mean, how to control this microcontroller is. So you have this microcontroller which is TIVA, and you need to connect it to the motor, and this motor itself will have this encoder A and encoder. There is encoder A, encoder B, which phase A and phase B, and these are the power to the encoder, and this is motor power. So basically, what the question says is like uh, when you connect the encoder and when this motor is moving, they are giving this value 4096 per second, and we need to convert. We need to get so this reading are being coming after connecting it to a microcontroller. This you need to make sense of this reading. What is this and how to convert it into RPM? So there is this specification which is given to you in the question one. Right? What was it? It is the PPR, which is 1024 pulses PPR. Okay. What it means is that the encoder specification is that it can sense up to a reading of 1024 pulses per PPR, pulses per revolution, right? So in one revolution, right? Okay, in one revolution can give up to a 1024 PPR, which is pulse per revolution. But when you convert it into a H per count, I've told you that each pulse can be counted as 4, right? In the quadrature encoder interface. So when you multiply it with 4, which is the 4096, right? This is what you will get in one revolution, and question it is given that H per count second. Okay. So when you just divide this term, number of revolution per second we will get. I mean, when you just divide this term, because it is one revolution, right? When you just divide it, you will get answer in the terms of number of revolution per second. Why we are dividing it? Right? Because this is how much we are getting at 1 second, but we want something in terms of revolution because it's RPM, revolution per minute, right? So how much it is giving in one revolution, which is 4096 multiplied for. You divide it, you will get something called 100 RPS, which is revolution per second. Okay, but we want to write it in RPM, that's why we multiplied with 60. So in this manner, you can calculate the RPM of a motor which is running. Okay, when you don't know the RPM of a motor, you can use this encoder to get the magnitude. This is how you get to calculate what is the velocity of encoder. And now coming to the question of PWM. So there was this question on PWM. So for PWM, uh, just go to the data sheet, and then there is chapter 20. Okay, in chapter 20, you need to go through this. I mean, Professor Gandhi has already told you about, but if you have any doubt, please again go through this chapter, and you will get to know this what is PWM timer, what is this PWM count down and count down mode, and count up and down mode. I think there's one question on PWM count up, and you can see that there's this question of count. This is in this manner you can just read through those pages of data sheet, and you can get to answer that answer this type of question. Okay. So let's just move on to our question. Just read. So observe the following diagram of the PWM module. Okay. Identify the values to be loaded on the following register. So again, it is asking for register. So whenever you heard about this term called register, the values always has to be loaded in terms of clock cycle. Okay. We need to have a 30% duty cycle on the PWM of channel A. Okay, so PWM A, they're having a channel A. So they're asking for 30% duty cycle channel A. The frequency of 10 kilohertz. Okay. The frequency of 10 kilohertz. Assume PWM clock frequency of 10 megahertz. Refer the appropriate data sheets. Okay, so this is the common sentence, and based on this, answer this. What should be the value of loaded on the load register? So you this load. There are three registers are there. Comparator A, comparator B, and load. Okay, load register, and you need to calculate what is the value we need to write in this time. So first of all, we need to understand what is this x-axis and what is the y-axis. What this graph actually tells you about. The x-axis here is basically the time period, time actually, micro to, and the y-axis here represent the clock cycle. Terms of clock cycle. Don't know what is the clock cycle, which type of clock cycle, but the clock cycle. So how to calculate this? Also, we need this value, which is from 0 to. Need to know what is load value which we write it. First of all, this is time. This is clock cycle. Okay, and so there is this term called PWM clock frequency. If you see it carefully, PWM clock frequency is 10 megahertz. Whereas if you heard in the last question, it is written the microcontroller frequency was for around 40 megahertz. So you see that the PWM clock frequency is a lot lower. Can anybody tell me like why it is lower than the microcontroller clock frequency? You can type it in the chat box. Question: why the microcontroller frequency is more and PWM frequency is like downgraded? Uh, Anybody? Said? Yeah, you have is this Mahima, this not a book actually. It's a data sheet. It's available. I've already told you, right? I mean, the start of the class. I think you joined very late. Do we have access to? Yeah, you have access to. I will show. So these data sheets are available in hands-on activities. And what you need to do is that section you will get this. Click on hands-on activity. If you this will get this. There's this folder called this Google share folder will open, and in the Tiva microcontroller have data sheet, and the data sheet you get this. And yeah, you have all have access to this PP I'm sharing you. Once you the problem solving session you will open. So this is the presentation folder link, and please answer this question: why the PWM clock frequency is lot lower? So because why it is lower? Because PWM clock frequency is a lot sensitive. Okay. So we downgrade it so that any we do not left any clock cycle. So there might be a slippage of one clock cycle. Okay, that's why we downgrade so that we make the precision will be made. That's why if the microcontroller clock will look like this, which is very fast. Because in case of here, in 4 microcontroller clock frequency will is equal to 1 PWM clock frequency. 4 cycle of microcontroller equivalent to 1 cycle of PWM pulse. 4 pulse is equal to 1 pulse of PWM. So here all this frequency which is 10 kilohertz. So 10 kilohertz is the frequency of the pulse. Okay. So this is basically clock. This clock you need to your PWM has to run. Okay. So it is written that it is a PWM signal on channel A with a frequency of 10 kilohertz. So, so the frequency given to you. Okay. And with this, so and this triangle you see is called carrier waves. Okay. And the frequency of this carrier wave is basically equal to the frequency of PWM. Okay. It is given here with 10 kilohertz. Okay. So basically the time period, right? The time period, and this is what 10 kilohertz. Okay. And this looks like an equilateral triangle to you. Okay. Okay, so if this is 10 kilohertz, it's not 10 kilohertz. This is an if you need to convert it into seconds. This is time actually. So what is 10 kilohertz will look like? I think it's around zero point 0.1 millisecond. I think. Not one. 1 millisecond. That's zero point 0.1 millisecond time basically. Okay, but when you convert, and this is in terms of clock cycle. Terms of clock cycle. So yeah, this is something look like an equilateral. So this is equilateral triangle. Okay, but so this is what a 10 kilohertz look like. And when you do this, and in the step up operation, what is step up? When you go from zero to load, this will take around point millisecond, can also be written as 100 microsecond. Okay, if its total is 100 microsecond, then it will be 50. The half will be 50 microsecond. So let's just so we need to get this value, which is a load register, and I've told you it has to be written in a clock cycle, but in PWM case has to be written in PWM clock cycle, not the microcontroller clock cycle, right? So what we need to write is, this is again I've made the same diagram. What you need to write is how much clock cycle it's taking from going from 0 to 100, right? That is load, and we know that it is 50 millisecond, right? This is 50 second because we know it. This is 50 millisecond. So what is the PWM clock cycle? So in 1 second, it's giving around 10 megahertz, I think. Yeah. And 50 millisecond, what it will be? The clock cycle. So in this, load value is counted up first and then down. Here the time. So when you go from 0 to 100, so 0 is like time is 0, actually, like a 0 clock cycle. And when you go to the upper part, which is up to load, is having some kind of a clock cycle. So hence the time counting up is 50 microseconds. So when you go from 0 to here, right, when you go from here to here, which is it is taking around 100 microseconds because of the 10 100. When you go from here to here, it is taking 150 millisecond. So how much clock cycle it is taking? So in 50 millisecond, 1 millisecond is equal to sorry, 1 second. 1 second is equal to 10 megahertz, right? One, because it's a frequency. And what how much time it will take to for 100 millisecond? Okay, just multiply it with that value, and you will get 500. Okay, and don't write that in terms of 5499, because the question it is given, it is decimal. Okay, so when it is written in decimal format, please change it to 500. Whenever it is said that it has to be written in binary, then only you need. Anybody have any problem with this to ask? Okay. And there will be a one follow-up question. I think it doesn't even. Okay. Wouldn't this lower the sensitivity of PWM? No, actually, Parth, it wouldn't, because I think will tell you the phenomena of how the PWM works. So thing is, your microcontroller is running at very fast. Okay, so your mostly PWM is required to run some kind of a motor. Okay, mostly motors, and these motors can take up to a frequency of around 1000 hertz, 1000 hertz, so 1000 hertz, 1000 hertz. If you to take any motor, like one of the fastest motor in the world also, they run at around 1000 to 10,000 hertz. Okay, the frequency of which they can operate is 10,000 hertz. Queuing. Okay, mostly, I mean, if you see whatever motor you see, is mostly will lie around 1000 to 2000. I'm actually exaggerating this part, but let's say 10,000 hertz. This is, if you, so why I'm saying this is because what PWM do is like, you have two terminals to a motor, right? When you send a 12-volt signal, basically you are sending some kind of a DC signal, right? And 12-volt, it is rotating at its rated RPM, right? And suppose you want to, instead of 50 RPM, you need to run at 40 RPM. What you will do is, you need to change this 12-volt to something around 8-volt, right? Basically, you need to change it analogically, but we don't have any option. So what we do, we use this PWM signal, right? What we do is we change the duty cycle. Okay, so this thickness, what is PWM? Pulse width thickness. So what we can do is, this is 50%. Suppose this is 5 volt, this is 0 volt. It's 50%. So when you run at 100,000 hertz, and when you send the signal to this part, it will interpret this signal as a half signal, because it's a 50% duty cycle, right? And when suppose you want to reduce the duty cycle to, suppose let's say 30%, this is what the signal is. And instead of 50%, it will look around, instead of giving 2.5 volt here, it will give around somewhat around 1 volt. Okay, so basically at the end of the day, we want to give them analog signal. Analog signal, you means uh, minus 12 volt here, plus 12 volt here. Okay, or plus 8 volt here, minus 8 volt here. And at the end of the day, we need to send them, send a signal of analog signal. Okay, and in order this machine to run at analog, the frequency needs to be very low. Okay, suppose if you send a frequency of, let's say, 40,000 megahertz. Okay, and will be, the frequency will be very fast. It will be very fast. I mean, the pulse rate will be very fast. Signal, the will not, when the power will put to this motor, it will not able to interpret, because anyway at the end of the day, it need to interpret as an analog signal. So in that, at the end, the motor needs to interpret the signal as an analog signal, and that can be only done at lower frequency. Okay, if you increase the frequency, the motor, it won't run. It will interpret as either a zero or either something else. It will be interpreted as zero, basically zero. It won't run, because the frequency is so fast, it can't able to interpret the signal. Okay, so to interpret the motor signal, that's why we downgrade the frequency. Okay, but I think I'm able to answer the question. I think I will check if you have any more doubt to ask in the chat. Okay, Parth, and let's just so this is the answer to the question, and let's get 36. There are two more questions I will take, and yeah, so they wants to ask any more.
Sir, one
Yeah,
more question I had
yeah,
regarding
Parth.
this PWM. So, sir, as you explained, if there is one particular motor I want to drive using this PWM interface,
Yeah,
So the higher limit to the pulse that we just showed, that you just described, say it will be 12 volt, the higher value, and the lower value will be 0 volt only.
Right.
So to manipulate this value, we just need to play with the average
Average
value
value.
which the controller will pick up, the
Right.
motor will pick up.
Right.
So we just change the the duty cycle,
Right.
the
Right.
time for which the high pulse will be sent into the motor.
Yeah. Yeah. That's
So
right.
I wanted to ask that will the amplitude, which is the upper limit, say for a particular motor, would remain 12 volt only for the whole application? It won't change, right?
Uh. Yeah. The
We just
that.
change the
Yeah.
pulse width in order to change the average
Average
value.
value. Right. Right. So the upper value will always remain 12 volt because it is the motor. It's the property or the motor is being made in such a manner so that it can operate in 0 to 12 volt only. The upper value always remain 12 volt only. When you send a signal using that, the motor itself will recognize, okay, the signal as 8 volt or 12 volt, 8 volt or 5 volt or 4 volt. The motor interpret that signal as the average value. That's what I'm saying. The upper value will remain 0 and 12 volt. The upper value will remain 12 volt only. The lower value will remain 0 volt only. Am I able to answer the question, or
Understood, sir.
yeah, or have any?
Yes, yes, yes.
Yeah. So, but in microcontroller, you mostly work on 0 and 5 volt. Okay. So for this, there is this something called. I mean, in my last class, if you, but there is this something called amplifier we use, which is called motor driver. The motor driver, what it will do is like it will amplify 0 to 5 volt to 0 to 12 volt. Okay, it will amplify 5 volt to a 12 volt. That's what. But in microcontroller, you just give it at 0 or 1 only. So let's just move on to a question. Question is related to duty cycle. I
So,
think
so this amplifier and PWM cannot be used.
fire and PWM cannot be. No, no. PWM is something which is
I mean,
related.
sorry to interrupt, sir, but I meant to ask. No, I meant to ask that this amplifier and PWM serve similar kind of purpose, so they aren't used at the same time, no? I mean,
No, no.
if you use a
They are
PWM, there's no need of an amplifier.
the amplifier also do something like that. I mean, but you see, all these microcontrollers, they only work on digit. I mean, it's a digital 0 or 5 volt only, like this, like this, like this. Only. Suppose instead of a microcontroller, you can use only amplifier. So that's what your question. So if you have an amplifier, okay, amplifier is there, and then there is a motor is there, and you want to run this amplifier, the motor, and you have some kind of a knob here, okay, and this knob will change like like a multiplication factor. So the can change the multiplication. So you are giving some kind of a 5 volt. The multiplication factor is somewhat around let's say 2, and you can change the multiplication factor by changing the knob. That way you can control a motor. What you need to do is 2 into 5 volt, 10 volt. It will run the motor at some 10 volt. Okay. What you need to, and again you change this multiplication factor, which is suppose around 1 point. Then also you, then 5 into 1.2, I think around 6, right? It's giving 6 volt. You can do that. But my motor driver is not. Motor driver is something. It's an amplifier. Of course, it's an amplifier, but you don't have that knob. Okay, okay, you don't have that knob so that you can rotate that knob. Okay, we can change that. It's an amplifier. It's a amplifier with a constant amplification factor. So in that case, we have an amplifier which convert 5 volt to 12 volt. Okay. So when you go through the shop and ask for a motor driver, you need to always ask how much amplification it can do. Okay, 5 volt to 12 volt or 5 volt to 24 volt. These are some specification which you. Okay. I think I'm clear. Let's just move on to the duty cycle part. So, so follow up to the next question is what should be the value of comp A? Okay. So this is comp A. Okay. So I'm telling you about the register level programming here. Okay. This is what sorry. Uh, yeah. So this was the question, right? What we need to do is basically we need to convert using this carrier signal into a PWM signal, right? And you see this PWM A here. So when you give some signal, when you give some kind of a value, let's say not to not to convert this whole signal to a 30% duty cycle, what is the value which is need to be given? So you give some value here, and it will intersect some. It's a comparator. It will check a value. Okay, if a value met, then it will send a signal like this. If a value met, it send a signal like this. And this is what the PWM signal is. Okay, if you change this width to here, this, then the width will change. The pulse width will change. Change to this, the pulse width will change. That is what here is happening, and that's what I am question. I wanted to get a duty cycle of 30% duty cycle. Okay, what is the comp A will be? That is what the question is about. Okay, so how to solve this kind of question? So if you have this, I think I've lost some. Am I sharing my? I Yeah, I think good now. It's visible. Yeah. So what I was saying is like we need to make this signal a 30% duty cycle signal. Okay, what signal we need to make a 30% duty cycle? This PWMA signal. Yeah. So this PWMA signal need to be 30%. So for that, this comp A need to change. Okay, so what is the value which we need to give to the register? That's what we need to calculate. Okay, so this is PWMA. How to What is the value? So load A value which is given to you, which is 500, right? What is the value which is comp A should be, so that the PWM duty cycle need to be changed? That is what the question is being asked, and how to solve this sort of a question. You need to use this simple mathematics. Okay, so for a 30% duty cycle, this is what a 30% duty cycle look like. This is 30%, is 100%. Okay, and we need to calculate what is x here. Okay, how to do it? Just make a similar triangle concept. Use a singular triangle concept. Have this. Okay, I don't. 500 minus x 500. So bigger triangle ratio minus lower triangle, smaller triangle ratio. This manner you can get x here. Okay. So 30%. This is how you get it. 500 by 100. 500 minus x by 30. It's easy, right? There is nothing more. This is how you get it. So x will be 350. When you put x equal to 350, so there will be two type of pulses will become here. So this will high pulse. Then similarly will go for other pulses like that. So when you change this 30% to 20%, let's say 30%, right? You go to when you go to 20%, you see the pulse changing here. Okay, the pulse width is this one. It's very small. As the duty cycle decreases, the pulse width also decreases. It's all about it. This is what how the microcontroller do the thing. This is what how microcontroller do the programming in itself. That is what I wanted to. Okay, and here is one of the other example you can see here. You see that we need to send something called a sine wave, right? How do we send it? So this triangle is basically the carrier wave which I have talked about, and this carrier wave has this comparator basically, and in order to send a sine wave, you need to send this kind of duty cycle so that you can get a sine wave. This is what the actual output which your microcontroller gave it to the motor. Okay, in order to generate a sine wave. So let's just move on to the next question. So next question is a simply theory based problem. So Robish, I think you've all heard about interrupts. Okay. What is interrupts? Interrupts. interrupts. I think this whole question. So robots try to fix a sampling time in microcontroller for implementation. Sampling time, you mean you know that what is sampling time, right? The time in which your microcontroller take readings. So what is the optimal way to do that? What is the robust way to do? First way is to write a program in an infinite loop with a delay. The problem with the delay is like you have this program which is running infinitely, and you also given some kind of a time here. Okay. But parallelly you are also running some programs. Okay. Parallelly you are also running some programs, kind of a loop. It's running paying data like data, and it's like running again and again. Has some kind of a delay, the delay, right? But the problem is parallelly there is one more program which is running. Okay, is also taking some clock cycle. There might be a chance that the delay which you have given, which is basically the sampling time, might get instead of 0.5 second delay, you will get something around 0.51 second delay. There might be an issue like that. Okay, for this, so you can't do this. The option is write a program using only hardware interrupts. No, interrupts are good, but not. We need to also give times also to write a program using interrupt along with the timer module. Timer module give the time. We cannot fix the sampling time. It will be happen as the code option. Answer C is right. It's a basically theory problem, but let's just move on to the next numerical problem here. So here again, it's a question on sorry encoder here. Only the index pulse of a rotary encoder is captured. So it's written that I've told you that there are three pulses, right, in encoder. There's one here, then there is pulse B here, right, has a 90% phase shift. Then there is one index pulse, which will pop up after every one revolution. Okay, after one revolution, this index pulse will, if one revolution has been done, it is then it is one pulse will come. Okay, what it does. So yeah. So what they want to know, the speed of the motor. They wanted to know what is the speed of the motor when index pulse is given. The speed of the motor shaft is 500 index as counted in one. So for 400 index pulse counted in 1 second, which means that 400 index pulse, one index pulse means one revolution, right? 400, basically it means that 400 revolution per second. We need to convert it into RPM, which is multiplied with 6 seconds, 1 minute. Will convert it, will give you the speed in basic. Multiply it with so the speed will be equal to 400 into 6 because it's, and there is one more simple question, the duty cycle of the PWM signal, if the pulse frequency is 100 hertz and pulse width is 0.07. So let's just say what is pulse frequency. This is 100 hertz. The pulse width is also given. What is frequency? Frequency is something where start from somewhere and get to a cycle. What a cycle looks like. Okay, this is the frequency when you just uh, reciprocal it, you will get a time period, right? Okay. The time period it will get it. There is 10 milli point 0.01 second, right? Time period because it is given, and the pulse width is given, which is around 0.0007. When you just take the ratio here, comes by this, you will get around 70%. This is how you get 70% duty cycle. This is the duty cycle. And then there is a question on interrupts, and I think after interrupt, I think we can let's just there's one more question on interrupts. So we would like to set up an interrupt service routine. ISR is basically something like you interrupt means interrupt is something like suppose for a small amount of time, suppose you're running a motor and for a small amount of time you want to get motor reading. Okay, so but it has to happen at a particular time period. For that we use interrupts, and when you write this interrupt service routine, we need to set a sample time. Okay, 5 milliseconds. Here it is written 5 milliseconds. So 5 millisecond, your loop has to stop. That stopping time will get an encoder reading. That is what interrupts will do here. And so several functions on an API library are used for this to set a sampling time function. So whenever this load set is given, need to always answer in terms of a clock cycle. Okay, that is one. So what should be the value of third argument timer load set? So it means that we'll set the timer of interrupt. What is the timer? It will be 5 microseconds, sorry, 5 milliseconds. Okay. And to get a sampling time of 5 milliseconds, considering the system clock frequency of 80 megahertz. So here the clock frequency is changed. Okay. So in 1 second, how much clock cycle it will give? 80 megahertz, right? But how much we want? We want up to something around 5 milliseconds, right? 5 milliseconds. So 85 milliseconds into 10 to the power 6. Power 6 is, and millisecond convert into seconds. It will be 200, right? I think the answer. This is how the answer. The answer. So let's just leave this part. There's some questions on modeling. Okay, this modeling question will help you to solve. I think there is one question called here. Okay. So I will just give you some definition about. I mean, it's a basic. Yeah. Just stay with me for 5 minutes. 5 minutes more. So derive a transfer function for DC motor model. Okay. What a DC motor look like? So DC motor is basically you need to derive a transfer function. What is transfer function? Transfer function is basically final parameter versus input parameter. So what is the final parameter? So if you have a motor, uh, motor is basically a electromechanical model. So this is what a electrical model look like. Okay, this is the circuit, and this is what a mechanical model look like. Mechanical is basically what the inertia of motor are, how much weight it can lift and all that, and this is what electrical circuit look. So we need to, so what is the, if we have a motor, what we give to the motor? We give motor input as a any kind of a, we give current to the motor, right? We give voltage, but voltage is almost, the current is changing. We give current to the motor, and what motor will give us? It will give us RPM. Then the dot. Okay. Basically, we want a transfer function. I think you know transport transfer function is the dot s on I dot s. What we want for a transfer function. For that, because theta dot velocity is something a mechanical term, and I is something electrical term. Okay, so we need to know the governing equation of both of the model. Okay, let's just look into the governing equation of a mechanical system look like. This is what a mechanical system is. Okay, so we have this J is inertia, and theta is a theta double dot is acceleration, and then there is a friction term. So basically it's a torque. How much torque a mechanical system gives? So how much torque the motor is exerting, dot theta. Okay, this is the equation of a mechanical system. Need to combine it with the electrical system here, which is basically what we are doing is we have this circuit here. Okay, and we have a motor here. This motor is connected to this the whole what is the mechanical system? The mechanical system is the load, basically what the load is. Okay, much load it has to lift. So what is this electrical system is, so when you apply this KVL, Kirchhoff voltage law. Okay, we just equate the voltage here. You have this L di by dt, which is the inductance part of the motor. So this is the inductance voltage. Then there is Ri. Ri is voltage due to resistance. Then is equal to V minus this voltage minus EMF. What can anybody tell me what is EMF is? I know EMF is electromotive force, but why that EMF is generated? So I think Michael Faraday in 1825 1825 to 40 around, he induced this term called EMF. I think in your 12th of the charge particles. So could you tell us where do we practice this book? So there is no reference book here. All these questions are generated by Professor Gandhi itself. It's a course. It's not we are taking. All these experiments are done at IIT Bombay itself. So there is no such. What I would recommend you go through the data sheets. Okay, so data sheets which I am referring to here. So data sheet of mostly PWM and QDI. Okay, don't need to go through every and each and every. Possible go to the interrupt also, but pulse width and quadrature will be enough. There are some numerical which is given inside it. Okay, so please go through it. And Mahima, because of charge particle. So EMF is electromotive force. I know it's not of a charge particle, so I will just tell you a brief about what the EMF and how it is been covered. So Michael Faraday, what he doing was like, yeah, he have this conductor. Okay, what he done was like he has this conductor and the current was running here, and what he did was like he have this metal bar, just like he just moved and this electric field this is electrical and magnetic field is generated. Okay, and when this magnetic field was generated, when he moved this object or a mechanical bar inside this magnetic field, he observed that there is a change in the current. Okay, due to this change in this current, this due to this change in the voltage, uh, that change in voltage itself is called EMF. Michael Faraday then only discovered the generator part. So Michael Faraday, uh, the guy who invented generator, dynamo basically. Okay, so this is what the Faraday. So what the Faraday law tells you, what the Faraday law tells you about EMF is equal to uh, RPM. That is the, I think phi is the magnetic field and is the pole and A. So this formula you have already in your so basically what it do is that how much velocity in which you are say the motor fin is running. Okay, so when you apply some kind of a voltage here, the motor will start to rotate. Okay, when motor start to rotate, it's basically cutting the magnetic field. So it's what it do is that due to the cutting of magnetic field, it induces a current. It induces a voltage, which is electromagnetic force. It induces a back EMF. Okay, that's what V minus EMF. Okay, so when you start a motor, when the velocity is zero, which is n, n is velocity. When velocity is zero, uh, your EMF is basically zero. Okay, so when you start a motor, you will need more power, more voltage. But when the motor is at very high speed, then in that case you don't need that much voltage. That's why there's this high voltage problems are there. Okay, so let's just come to back to the question itself. So what is this? This is EMF. EMF and all this, the magnetic field Z. Z is basically number of poles. All these are constant. We refer it as Ke is equal to theta dot. Theta dot is RPM. Okay. To have this thing, just put it here. Okay, and you will have this. Here is there is theta dot, there is theta dot. There is a connected term in which, okay, so you just what you need to do is you just need to equate this term So put this theta dot term equal to here and put it in this equation one. Okay, and there is this something term called Lorentz law. What Lorentz law is that Lorentz law you also heard FL is equal to phi magnetic field, L is the length of the vector, and I think L is inductance. And when you connect it to torque, which is R into F, this is what the torque is converted into a current here. Okay, this you just need to go through this. Okay, so you just put it here, torque is here, and when you put it all over here, you'll get something like this. Applying Laplace. So I mean, I've not told. So when you just put torque I, so I is here, okay, and then theta dot will be equated using this term, okay. So you will all be left with I and theta dot, okay. So this is what the final equation will look like, and when you apply a Laplace on both sides, this is what you will get, and you just replace it. What you get theta dot by voltage. Voltage is the so they have done here is yeah. So instead of EMF, it has to be IA. Sorry, or V minus. Here it's not V actually. It has to be theta dot by. What do you need? Applying Laplace. So what they have done is like they apply a Laplace on both the equation. The first is the mechanical equation, okay? Second is the electrical equation. And what they did was after that they did theta dot is. They take this theta dot is, theta dot s, they put it here, okay? Like I they did, and they wanted basically. Oh, sorry, I think not voltage. It so velocity versus voltage. This is what you want to do today, and this is what the transformation. What the transformation look like? That basically will help you to solve this kind of. These are something for the governing equation they have told you, and only they to solve this kind of EMF constant. This EMF constant, you will get it like this by Faraday. K is EMF constant. It is like a torque constant. If you have any problem, please ask me, and I will. Yes, do anybody have any problem?
Sir,
Yeah, 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 Parth.
so for sir, if we need to enter the value in the register, so it needs to be in binary. So we
Yeah,
just subtract the answer, whatever we got, the decimal answer with one, and
yeah,
the
with
answer what we get, we enter that only.
yeah, yeah, you are right. Binary, you just need to minus it with one. Binary, you also consider zero as
Got it, sir.
will